Imagine waking inside a silent spacecraft and realizing you no longer know where Earth is, or whether you are still traveling through the solar system at all. Tonight, we'll explore 100 astonishing scientific facts about what truly happens when a human becomes lost in deep space. Please help Sleepy Space reach 1,000 subscribers by liking the video and subscribing. It may seem like a small gesture, but it means so much to me. Thank you. Imagine opening your eyes inside a spacecraft and discovering that nothing appears wrong. The cabin lights are steady, the ventilation fans are whispering through the walls, and beyond the window, the stars remain scattered across the darkness with an almost ceremonial calm. Yet the navigation display no longer agrees with itself. The last reliable position has vanished, and for the first time, you cannot say with confidence where Earth lies, how far away it is, or whether your present course is carrying you toward home or farther into the night. This is the first and most important truth about becoming lost in deep space. The experience would probably not begin with violence, but with uncertainty. There is no universal boundary at which ordinary space suddenly becomes deep space, because the term changes with context. Engineers may use it for regions far beyond Earth orbit, where familiar navigation systems weaken. Mission planners may define it through communication architecture, and scientists may speak more broadly of the space between planets, or beyond the dominant operational environment of Earth. But from the perspective of a stranded traveler, deep space begins at the point where the surrounding universe no longer provides intuitive guidance, where the tools that once translated motion into a safe route have failed, and where the human senses are almost useless. On Earth, direction feels natural, because gravity is always performing quiet geometry beneath your awareness. It draws objects toward the ground, gives the inner ear a persistent reference, defines what you call upright, and places a horizon around your field of vision. Even with your eyes closed, you usually know whether you are standing, leaning, or falling, because the vestibular organs of the inner ear respond to acceleration and orientation relative to gravity. In a freely falling spacecraft, however, you and the vehicle are accelerating together under the influence of gravity, producing the condition commonly called microgravity, and the body no longer receives the familiar downward signal that organized nearly every movement of your life. There is no absolute up or down waiting outside the hull. Those directions exist only relative to a chosen object, coordinate system, or local gravitational environment. The ceiling could become the floor merely because you turn your body, while the stars outside remain indifferent to the change. Nor is there a natural horizon. The horizon on Earth is not simply a beautiful line. It is a powerful geometric cue created by the curvature and surface of a nearby world. Remove that world from view, and the visual system loses one of its oldest anchors. A spacecraft may be rotating slowly enough that the motion is difficult to notice, and without a stable reference, the cabin can seem perfectly still. This is why losing direction in space is not equivalent to becoming lost in a forest or at sea. A sailor may read the sun, feel the wind, follow waves, observe clouds, or estimate latitude from the stars. A spacecraft in deep space may see the sun and stars with extraordinary clarity, yet still lack the information required to return home. The distinction begins with a basic principle of mechanics that Galileo explored and Newton later formalized. Uniform motion cannot be detected from inside a closed system without reference to something outside it. If the spacecraft is moving at a constant velocity, no experiment involving ordinary objects floating inside the cabin will reveal that velocity. A released tool will not be swept backward merely because the ship is traveling at tens of kilometers per second. It will continue beside you because it already shares the spacecraft's motion. You can feel acceleration when an engine fires, a thruster pulses, or the vehicle begins to rotate, but you cannot feel steady speed itself. This makes the first moments of disorientation unusually deceptive. The ship may appear motionless while crossing millions of kilometers because speed is not a substance pressing against the hull. It is a relationship between positions measured over time, and every value depends on the frame of reference chosen. Relative to Earth, the spacecraft may have one velocity. Relative to the Sun, another. Relative to the center of the Milky Way, something larger still. None of these is the single absolute speed of the vehicle, because modern physics does not provide a privileged universal state of rest. A navigator must therefore ask not merely how fast the ship is moving, but how fast relative to what. The stars seem like an obvious answer, yet the night sky is a subtle instrument. Most stars are so distant that their apparent positions change only slightly as a spacecraft moves across the solar system. Their patterns are excellent for determining attitude, the three-dimensional orientation of the vehicle. Because a star tracker can photograph a field of light, compare it with an onboard catalog, and calculate which direction the spacecraft is facing. But orientation is not location. A camera may tell you that the high-gain antenna points toward a particular constellation, while revealing almost nothing about whether the ship is 10 million or 100 million miles from Earth. The difference is fundamental. Attitude describes the rotation of the spacecraft, often represented by three angles, a rotation matrix, or a quaternion designed to avoid mathematical singularities. Navigation requires something larger, a state vector containing three spatial coordinates and three velocity components. In simplified form, these 6 numbers describe where the ship is and how its position is changing. If even one component is poorly known, predictions of the future path begin to spread into a growing region of uncertainty. That is why simply finding Earth through a window would not completely solve the problem. Seeing Earth might provide a line of sight, but a line alone does not supply the full distance, and distance alone does not provide the velocity perpendicular to that line. A spacecraft could appear aimed toward Earth while moving sideways fast enough to miss it by millions of kilometers. Pointing the nose toward home would not automatically turn the trajectory toward home either, because orientation and motion are independent in vacuum. A ship can rotate until its windows face backward, while its center of mass continues along almost the same path. Only a force acting over time changes velocity, and only a properly calculated change in velocity, known in mission design as delta V, can reshape the orbit. Before such a maneuver can be planned, however, the crew must determine the current state with enough precision to avoid making the situation worse. This is where the calm image of a map with a bright dot becomes misleading. Space navigation is not usually a matter of knowing one exact point. It is a matter of estimating a probability distribution from imperfect measurements. Each sensor has noise. Each clock has finite stability. Each catalog contains uncertainty. Each mathematical model neglects forces too small to include perfectly. Engineers, therefore, describe the spacecraft not only by a best estimate of position and velocity, but also by a covariance matrix that expresses how uncertain those quantities are and how their errors are related. In ordinary language, the ship is not known to occupy a perfect dot. It is believed to lie somewhere within a three-dimensional region whose shape may stretch and rotate as time passes. A small velocity error is especially dangerous because it accumulates. If the true velocity differs from the estimate by only 1 meter per second, the position error grows by roughly 86 kilometers after 1 day, more than 2,000 kilometers after a month, and far more over longer intervals, even before gravitational effects complicate the path. The mathematics becomes richer because a spacecraft is rarely moving through an empty Euclidean stage untouched by outside forces. The sun, planets, moons, and smaller bodies all contribute gravitational acceleration. Newton's inverse square law provides the basic framework, with gravitational strength weakening in proportion to the square of distance. But real navigation often becomes a many-body problem in which no simple, closed-form solution describes the entire journey. Numerical integration is used instead, advancing the state step by step through time while accounting for known forces. General relativity may also be included where the required precision makes its corrections relevant, particularly in timing and high-accuracy orbit determination, though Newtonian mechanics remains an excellent approximation for much of spacecraft operations. Even forces that seem almost poetic in their weakness can matter. Sunlight carries momentum and exerts radiation pressure. Heat emitted unevenly from the spacecraft can produce a tiny recoil. Gas leaking from a valve may provide an unintended thrust. A wheel used to control orientation can accumulate angular momentum until it requires correction. None of these effects would throw the ship suddenly across the solar system, but deep space navigation is a science of small influences, given long periods in which to act. The history of exploration is filled with reminders that the universe does not need a large force to create a large discrepancy. It only needs time. The so-called pioneer anomaly, once discussed as a possible sign of unfamiliar physics, was eventually explained largely through the subtle recoil produced by anisotropic thermal radiation from the spacecraft, an elegant example of how heat leaving a machine can alter its motion by an amount tiny in each moment, yet measurable across years. If your navigation system failed, the stars could still restore attitude. The sun could provide a directional reference, and sightings of planets might help reconstruct position through angular measurements and orbital models. But the solution would not be immediate. A single observation might permit many possible trajectories. Repeated measurements over time would gradually narrow them. Filters used in navigation, including variations of the Kalman filter, combine predictions from physical models with new sensor data, weighting each according to its expected uncertainty. The result is not certainty in the philosophical sense, but an estimate refined enough to guide action. Until that estimate becomes trustworthy, firing the engines may be more dangerous than waiting. A correction performed in the wrong direction can enlarge the miss distance, consume irreplaceable propellant, and transform a recoverable error into a permanent one. So the first emergency procedure would be strangely restrained. Stabilize the spacecraft, preserve power, confirm the clock, identify the star field, check the inertial sensors, inspect stored navigation data, and resist the instinct to act, merely because silence feels unbearable. In deep space, patience can be a form of precision. The crew would need to separate several questions that human intuition usually blends together. Which way is the ship facing? Which way is it actually traveling? How quickly is that velocity changing? What gravitational bodies dominate the local motion? How old is the last reliable state estimate? How rapidly is the uncertainty expanding? Only after those questions begin to resolve can the word home acquire mathematical meaning again. And this is the deeper reason the opening stage of being lost would feel so uncanny. Earth would not necessarily be hidden. It might exist as a bright point somewhere in the blackness, carrying oceans, cities, voices, and every familiar horizon you have ever known. Yet, a visible destination is not the same as a reachable one. Between you and that pale point lies not merely distance, but geometry, momentum, timing, and the quiet authority of physical law. The spacecraft continues onward whether or not its crew understands the path, and the stars offer orientation without rescue, beauty without scale, and light that may have traveled for centuries only to tell you which way you are facing. They do not tell you where you are. They do not tell you how fast you are leaving. And as the instruments begin the slow work of rebuilding those answers, the first true realization settles over the cabin with the softness of falling dust. You are not lost because the universe has become chaotic. You are lost because it remains perfectly ordered, while your knowledge of your place within that order has become incomplete. Once the spacecraft has recovered enough orientation to know which way its instruments are facing, a quieter and more difficult question begins to fill the cabin. Where will the ship go if no engine is fired, no command arrives, and nothing is done except to let the darkness carry it onward? The simplest answer is also the one that most deeply contradicts ordinary human experience. The spacecraft will not gradually slow down and come to rest. It will continue along the path determined by its present position, its present velocity, and every force acting upon it. Because motion in space does not require a continuous push. On Earth, nearly everything that moves eventually stops because energy is carried away by friction, turbulence, deformation, and heat. So the mind grows accustomed to treating rest as the natural ending of motion. Yet Galileo's studies of inertia, later expressed more completely in Newton's first law, revealed that rest and uniform motion are physically equivalent states when no net force distinguishes them. A spacecraft coasting through deep space is not spending fuel to maintain speed. Its engines may be silent, its tanks closed, and its machinery almost asleep, while the entire vessel crosses tens of thousands of miles during a single quiet hour. If all external forces could somehow be removed, Its center of mass would follow a straight line at constant speed through an inertial frame. But the solar system is not an empty geometric chamber, and no spacecraft within it is completely free from influence. The Sun's gravity reaches across the planetary system. The planets add smaller but sometimes decisive perturbations. Distant bodies contribute still weaker accelerations, and even sunlight presses gently against the hull. So the true path is usually curved, though that curvature may be too gradual to perceive through a window. The basic shape of the journey can be understood through the union of two historical discoveries: Kepler's observation that planets follow ellipses with the Sun at one focus, and Newton's demonstration that these paths arise naturally from an inverse square gravitational force. Under an idealized two-body model, where only the spacecraft and one dominant celestial body are considered, every unpowered trajectory belongs to the family of conic sections. If the spacecraft's total orbital energy is negative, it follows a bound ellipse and will continue circling the dominant body. If that energy is exactly zero, the limiting path is parabolic. If the energy is positive, the trajectory is hyperbolic, allowing the spacecraft to recede indefinitely from that body, although it may still remain gravitationally bound to a larger system. This classification can be expressed through the specific orbital energy, commonly written as epsilon equals 1/2 the speed squared minus the gravitational parameter divided by distance, or epsilon equals v squared over 2 minus nu over r. The first term represents kinetic energy per unit mass, while the second represents gravitational potential energy per unit mass, and the balance between them quietly determines whether the ship will return, circle, or escape. Distance alone cannot reveal the answer. A vessel far from the Sun may still be bound if it is moving slowly enough, while a vessel much closer may already possess sufficient speed to depart on a hyperbolic route. The familiar idea of escape velocity emerges from the special case in which the total energy becomes zero, giving a threshold speed proportional to the square root of twice the gravitational parameter divided by distance. Yet, escape velocity is not a rigid wall in space, nor does crossing it cause gravity to disappear. It simply means that, under the assumptions of the model, and without further propulsion, the object has enough kinetic energy to continue outward without being turned back by that particular body. Even an escaping spacecraft continues to decelerate as it climbs through the gravitational field, surrendering kinetic energy while gaining gravitational potential energy. And its speed at great distance approaches a remaining value known as the hyperbolic excess velocity. Mission designers often denote this quantity as V infinity, not because the ship literally reaches infinity during the mission, but because it describes the asymptotic speed left after the central body's gravitational influence has become comparatively weak. If the lost ship is somewhere between the planets, its motion may be approximated as an orbit around the Sun, and the most likely outcome is not that it will fall straight inward or fly directly outward, but that it will continue along a solar orbit whose size and shape were already encoded in its state of motion at the instant navigation was lost. A spacecraft traveling slightly faster than the local circular velocity may enter an ellipse carrying it farther from the Sun before it eventually turns back. A slightly slower spacecraft may descend toward a smaller orbit, gaining speed as gravitational potential energy is converted into kinetic energy. This produces one of orbital mechanics' most counterintuitive truths. To move inward toward the sun, a ship often begins by slowing down, while to reach a higher orbit, it usually begins by speeding up. The burn does not push the craft directly into its final destination. It changes the shape of the orbit, allowing gravity to guide the remainder of the journey. If no burn occurs, the existing orbit continues, and the vessel may return to the same region of space after one orbital period, though not necessarily when a planet is there to meet it. Orbital motion is therefore not merely a question of crossing locations, but of arriving at those locations at the correct time. Earth itself is moving around the sun at nearly 30 kilometers per second. So home is never waiting at a fixed point. By the time a stranded spacecraft reaches Earth's former position, the planet may have traveled hundreds of millions of kilometers along its orbit. This is why pointing the nose toward the blue point in the distance does not create a return trajectory. Rotation changes attitude, not translational velocity. The spacecraft may turn through 180 degrees while its center of mass continues almost unchanged along the original path, like an ice skater spinning while gliding across a frictionless surface. To alter the orbit, the engines must generate thrust, and thrust must act long enough to create a measurable change in velocity. The accumulated change is called delta V, one of the central currencies of spaceflight. Delta V is not the same as fuel mass because the amount of velocity change obtainable from a given quantity of propellant depends on engine efficiency, vehicle mass, and how much mass remains after each burn. The Tsiolkovsky rocket equation, delta V equals VE natural log of m0 over mf, captures this severe relationship. Available delta V grows with exhaust velocity and with the logarithm of the ratio between initial and final mass. The logarithm is unforgiving. Doubling the desired delta V does not merely double the required propellant. Depending on the engine, it can demand a dramatically larger mass ratio. A lost ship may therefore have tanks that appear partly full, yet still lack the delta V needed to erase its existing momentum and establish a safe return orbit. The idea of simply turning around becomes especially misleading at high speed. If the vessel is moving away from Earth at 20 kilometers per second in a chosen frame, canceling that motion alone requires approximately 20 kilometers per second of delta V, and returning with a comparable inward speed may require another large maneuver. Before accounting for gravitational geometry, braking near Earth, navigation corrections, and reserves. Real mission planning searches for more economical paths through orbital timing, planetary encounters, and carefully placed burns, because brute force reversal is usually beyond the capacity of chemical propulsion. The location of a burn also matters. A small velocity change near periapsis, where the spacecraft is moving fastest and deep within a gravitational well, can produce a disproportionately large change in orbital energy, an effect associated with the Oberth principle. The same amount of propellant used at another point may reshape the orbit less effectively. Yet, exploiting such opportunities requires precise knowledge of the trajectory. Uncertainty transforms efficiency into risk. A burn made minutes too early at the wrong angle, or with an incorrect estimate of velocity, can shift the future path by enormous distances. In the early days of interplanetary navigation, engineers often simplified these trajectories using patched conic approximations, treating the spacecraft as moving primarily under the gravity of one body at a time. Then, mathematically joining the separate arcs as it passed from the region dominated by a planet to the region dominated by the Sun. This method remains useful for planning and intuition, but the boundaries involved are not physical walls. A planet's sphere of influence is an analytical convenience, usually defined according to a comparison between gravitational effects. Crossing it does not switch one gravitational field off and another on. Every mass continues to exert gravity, although one contribution may become so small that ignoring it produces an acceptable approximation. A related region, the Hill sphere, describes where a smaller body can retain satellites against the tidal influence of a larger primary. But it, too, is a model-dependent boundary, rather than a shell visible in space. If the drifting ship passes near a planet, the encounter may bend its heliocentric path through a gravitational assist, exchanging energy and angular momentum with the planet in a way that changes the spacecraft's speed relative to the Sun, while conserving the energy of the broader system. The planet's own motion supplies the changing reference geometry, though the alteration in the planet's orbit is immeasurably small for ordinary spacecraft. Such an encounter could help or harm a lost vessel, but accidental capture by the planet would generally require some mechanism for losing energy, such as atmospheric drag, propulsion, interaction with a third body, or an unusually favorable temporary capture geometry. Gravity alone in an ideal two-body flyby bends the trajectory, but does not permanently trap an incoming object that began with positive energy relative to the planet. The emptiness between planets also means there is almost nothing to bring the ship gently to a halt. The interplanetary medium contains plasma, dust, neutral atoms, and magnetic fields, yet its density is vastly lower than any terrestrial atmosphere. Drag exists in principle, but for a conventional spacecraft over human timescales, it is generally too weak to provide meaningful braking far from planets. Instead, smaller forces accumulate almost invisibly. Solar radiation pressure changes as the inverse square of distance from the Sun, and acts differently depending on the spacecraft's area, reflectivity, and orientation. Thermal photons leaving warm surfaces produce recoil. A slow propellant leak can apply continuous thrust. Outgassing from materials may alter both rotation and translation. These effects are modest, but a deviation of only a fraction of a millimeter per second, accumulated or misestimated over years, can become scientifically important. The spacecraft's future is therefore not a simple line drawn through darkness, but a numerically integrated solution, evolving through a landscape of forces, with each calculation carrying uncertainty from the measurements and models beneath it. In a full N-body treatment, the positions of the Sun, planets, moons, and perhaps selected asteroids are advanced together, often with relativistic corrections and detailed force models when precision demands them. Chaotic sensitivity can emerge during repeated close encounters, meaning that very small initial uncertainties eventually produce substantially different long-term outcomes. Though over short operational periods, many trajectories remain predictable enough for navigation. If the ship is never recovered and possesses enough heliocentric energy to escape, it will not become motionless after leaving the planetary region. It will enter the gravitational environment of the Milky Way, carrying the sun's galactic motion along with its own smaller departure velocity. The spacecraft would then orbit the galactic center as part of a vast population of stars, gas, dust, planets, and wandering objects. While passing stars could alter its path over immense spans of time. But long before those distant encounters matter, the immediate truth inside the cabin is simpler and more urgent. The vessel is already committed to a curve. Its engines can modify that curve only within the narrow budget allowed by remaining delta V, and every hour of uncertainty carries it farther along a trajectory that cannot be paused. The ship is not waiting to learn where it will go. It is already going there, silently, continuously, obedient to momentum and gravity, while the crew must discover whether the path ahead is an ellipse that may one day return, a hyperbola opening toward interstellar night, or a near miss whose distance from home will widen until Earth becomes only another moving light among the stars. If the spacecraft is still alive, if its cameras can still open their electronic eyes and its clocks have not drifted too far into error, then being lost does not necessarily mean remaining lost, because position in deep space can be reconstructed from light, time, motion, and patience, although never from a single clue and rarely with the simplicity of a glowing marker on a map. The first task is to determine attitude, the exact orientation of the spacecraft in three-dimensional space, and for this, the crew would turn to instruments descended from one of the oldest human practices, reading the stars. A modern star tracker is not a telescope in the poetic sense, but a precision camera linked to a catalog containing the measured positions and brightness patterns of thousands of stars. It photographs a small field of sky, identifies geometric arrangements among the points of light, and compares those arrangements with stored patterns until it solves for orientation. The result may be expressed through a quaternion or a rotation matrix, mathematical forms that describe how the spacecraft's body-fixed axes are rotated relative to an inertial celestial frame. Quaternions are especially useful because they avoid the singularities that can appear when orientation is represented only by three sequential angles. Yet this elegant calculation answers merely which way the vehicle is facing. It does not reveal where the vehicle is located, because the same constellation can be seen from widely separated regions of the solar system with almost no visible change. A sun sensor adds another reference by measuring the direction of sunlight, and coarse versions may restore basic control after a failure, while fine sensors can support more accurate pointing. But a single ray from the sun defines only a direction, not a unique point. Any location along that ray could produce nearly the same measurement unless other information is available. The spacecraft must therefore move from attitude determination into celestial navigation, a deeper problem in which angular observations are combined with time and orbital dynamics. If the onboard clock is reliable and the positions of the planets are known from an ephemeris, the apparent directions of the Sun, Earth, Mars, Jupiter, or selected asteroids can become geometric constraints. An ephemeris is more than a calendar of where bright objects appear in the sky. It is a numerical prediction of their positions and velocities in a defined reference frame at specific times, built from observations, dynamical models, and decades of refinement. Ancient astronomers created tables for the motions of the sun, moon, and planets, while later navigators used lunar distances and stellar altitudes to estimate position at sea. Deep space navigation extends that heritage into a realm where the ocean has no surface and the horizon has disappeared. The spacecraft may measure the angle between a planet and a background star, or between the visible limb of a planet and the center of a camera frame, and each measurement restricts the range of possible locations. Yet, an angle alone usually describes a surface of possibilities rather than a single solution. A line of sight toward Earth tells the navigator the direction in which Earth lies, but without range, it cannot say how far away the spacecraft is, and without repeated measurements, it cannot fully determine lateral velocity. This is why navigation is built from sequences. As the spacecraft moves, the same celestial bodies shift slightly against the distant stellar background, creating parallax, and the rate and direction of that change carry information about the ship's position and motion. Nearby objects are especially valuable because their apparent directions vary more strongly with the observer's location. A distant star provides an almost fixed reference. A planet, moon, asteroid, or comet provides a moving landmark whose geometry can reveal where the observer must be. When a spacecraft approaches a target world, optical navigation often becomes increasingly powerful. Engineers identify the center of the planet, its illuminated crescent, its moons, or surface features, then compare the observed image with predicted geometry. The spacecraft does not need to understand the image as a human landscape. It needs only the measured relationship among pixels, angles, time, and the known motion of the target. Farther away, however, optical measurements may remain too ambiguous to recover the full state quickly, and radio becomes the invisible ruler stretching back toward Earth. Ground stations can transmit a coded signal to the spacecraft, which returns or retransmits it, allowing controllers to measure the round-trip light time. Since electromagnetic waves travel through vacuum at the speed of light, the delay yields a range estimate after corrections for station location, hardware delays, planetary atmospheres, interplanetary plasma, and relativistic effects. A simple multiplication of time by light speed would be insufficient at high precision because Earth rotates while the signal travels. The receiving antenna moves, the spacecraft moves, and the path may pass through media that alter the signal slightly. Doppler tracking supplies another piece of the state. If the spacecraft is receding, the received radio frequency is shifted downward. If it is approaching, the frequency is shifted upward. The fractional shift is related to the line of sight velocity, and measurements accumulated over time can reveal extraordinarily small changes in motion. Yet Doppler is most sensitive to velocity along the radio beam and less direct about motion across it, so range, angular tracking, and dynamical modeling must work together. Some systems also use a technique known as delta differential one-way ranging, in which widely separated antennas observe the spacecraft signal relative to a distant quasar, whose position is precisely known. The difference in arrival time between stations helps determine the spacecraft's angular position on the sky with great accuracy, turning the Earth itself into a vast interferometric baseline. If contact with Earth is unavailable, the ship must rely more heavily on autonomous navigation. One possibility is to observe multiple solar system bodies and solve for the position that best matches all measured angles at the known time. Another is to use pulsars, rapidly rotating neutron stars, whose beams sweep through space with remarkable regularity. In particular, some millisecond pulsars emit stable pulses in X-rays, and a spacecraft equipped with suitable detectors could compare the arrival phases of pulses from several pulsars with predicted timing models. Because the spacecraft occupies a different position from the assumed reference point, the pulses arrive slightly earlier or later, and those timing offsets can be converted into spatial constraints. The analogy to GPS is tempting but incomplete. GPS satellites broadcast synchronized signals from known moving transmitters near Earth, whereas pulsars are natural sources at immense distances. Their signals are much weaker, and their timing models require careful correction for intrinsic spin changes, binary motion, propagation effects, and the motion of the observer. Pulsar navigation has been demonstrated experimentally and remains an active area of development, especially for future autonomous missions far from Earth. But its achievable precision, detector mass, observation time, and operational complexity depend strongly on mission design. The ship's clock would be central to every such method. If time is wrong, the predicted planetary positions are wrong, the expected pulse phases are wrong, and the translation from signal delay to distance becomes distorted. A clock error of 1 microsecond corresponds to roughly 300 meters of light travel, while a millisecond corresponds to about 300 kilometers. So timing stability becomes navigation accuracy. Atomic clocks reduce drift by tying timekeeping to stable quantum transitions. But no clock is perfectly immune to environmental effects, aging, radiation, temperature variation, or calibration error. Precision navigation also requires relativity, not because the ship is necessarily moving close to light speed, but because clocks at different velocities and gravitational potentials do not accumulate time at exactly the same rate. Special relativity predicts that a moving clock runs more slowly relative to a chosen frame, while general relativity predicts that a clock deeper in a gravitational field runs more slowly than one farther away. These differences are small, yet modern navigation systems are precise enough that ignoring them would allow errors to grow. The same principle already governs satellite navigation near Earth, where relativistic corrections are essential to prevent position estimates from drifting rapidly. Once all available measurements have been gathered, the spacecraft still does not simply solve one neat equation and obtain a perfect answer. Instead, it performs orbit determination, fitting a dynamical model to observations that are incomplete and noisy. The state vector may contain position and velocity, but advanced models can also estimate clock bias, sensor bias, small unmodeled accelerations, thrust scale factors, or other uncertain parameters. A filter such as the extended Kalman filter begins with a predicted state and its covariance, propagates both forward through the equations of motion, then updates them when new measurements arrive. If an observation agrees closely with the prediction and is known to be precise, it pulls the estimate strongly. If the measurement is noisy or inconsistent, it receives less weight. More sophisticated methods may include unscented filters, particle filters, batch least squares estimation, or smoothing techniques that reconsider earlier states after later data become available. Each approach reflects the same quiet idea. Navigation is not the removal of uncertainty, but the disciplined narrowing of it. The spacecraft's possible location may begin as an enormous volume extending across millions of kilometers, then contract as each observation removes trajectories that no longer fit the evidence. Correlations matter because an error in one component may imitate an error in another. A slight clock bias can resemble a range offset. A small, unmodeled thrust can resemble a velocity error. A mistaken estimate of a planet's position can shift the inferred spacecraft state. Observability, the mathematical degree to which hidden state variables can be recovered from available measurements, therefore depends on geometry and time. If every observation comes from nearly the same direction, some components remain weakly constrained. As the spacecraft and celestial bodies move, the changing geometry can reveal dimensions that were previously hidden, meaning that waiting for a better baseline may sometimes improve the solution more than collecting many nearly identical measurements. This creates a delicate tension inside the lost ship. The crew wants an answer immediately, yet the universe may require a longer arc of observation before the correct trajectory separates itself from the false ones. A hasty engine burn would corrupt the very motion being measured and introduce additional uncertainty unless the thrust were precisely characterized. The wiser strategy may be to stabilize the craft, record star fields, time planetary sightings, listen for pulsars, preserve every clock reading, and allow mathematics to gather shape from the darkness. The final result would still not be a luminous point of certainty, but an estimate accompanied by an error ellipsoid, a region describing where the spacecraft is most likely to be and how that uncertainty is distributed through space. If the ellipsoid becomes small enough, a course correction can be designed. If it remains stretched across incompatible trajectories, the ship may know the direction of Earth and still not know how to reach it safely. Yet the possibility of recovery remains, because deep space is not devoid of landmarks. Its landmarks are simply written in forms the senses cannot read unaided. The stars provide orientation, planets provide parallax, radio provides distance and velocity, pulsars provide timing geometry, and gravity supplies the equations that connect one moment to the next. Slowly, almost tenderly, the lost spacecraft can rebuild its place in the cosmos, not by discovering a sign that says you are here, but by listening to the faint agreements among light, motion, and time, until the vast field of possible locations narrows toward one silent, defensible answer. The moment the spacecraft finally understands that it is lost, its most urgent human impulse would be to speak, to gather every fragment of its condition into a message and send that message toward the distant point called home. Yet the call would not cross the darkness like a voice in an ordinary room. Because the universe permits information to travel no faster than light in vacuum, approximately 299,792 kilometers per second, a velocity so immense on Earth that it appears instantaneous, and so limited across interplanetary space that silence begins to acquire measurable depth. From the Moon, a radio message needs about 1.3 seconds to reach Earth, making a natural conversation awkward but still recognizable. From Mars, depending on the changing positions of the two planets, the one-way delay is commonly measured in minutes. From the neighborhood of Neptune, it is measured in hours. And from a spacecraft drifting far beyond the known planets, a single transmission may spend most of a day traveling home before the first receiving antenna can even know that it was sent. This delay is not caused by weak equipment, bureaucratic hesitation, or an inefficient network. It is built into space-time itself. If the lost ship sends a distress call that requires 10 hours to reach Earth, controllers cannot reply until the message arrives, and their answer requires another 10 hours to return. So even an immediate response belongs to a conversation separated by at least 20 hours. During that interval, the spacecraft continues moving. Its systems continue aging, and every instruction prepared on Earth is necessarily addressed to a version of the ship that existed in the past. A command telling the crew to examine a failing valve may arrive after the valve has been repaired, isolated, or lost entirely, while telemetry received on Earth describes conditions that may already have changed beyond recognition. Distance, therefore, transforms communication from dialogue into a sequence of carefully written letters, each crossing an ocean that cannot be shortened by urgency. The radio waves carrying those letters are oscillating electromagnetic fields, and in empty space they propagate outward without requiring air. Yet they do not remain concentrated as they travel. Unless an antenna shapes the transmission into a narrow beam, the energy spreads across an expanding surface whose area grows approximately with the square of distance. So the received power generally falls according to the inverse square relationship. Double the range, and a receiving system intercepts roughly 1/4 of the power under otherwise comparable conditions. Multiply the range by 10, and the received power falls to about 1/100th. In engineering form, the Friis transmission relation connects received power with transmitter power, antenna gains, wavelength, and distance, revealing that deep space communication is not merely about shouting more loudly, but about directing energy efficiently and gathering an almost vanishing fraction of it at the other end. The spacecraft's high-gain antenna acts like a carefully shaped mirror for radio waves, concentrating transmitted power into a narrow lobe rather than allowing it to disperse equally in every direction. This gain makes communication across billions of miles possible, but it creates a severe geometric demand. The narrower the beam, the more precisely the antenna must point. A spacecraft may possess a functioning transmitter and sufficient electrical power, yet remain unheard because its antenna is aimed a fraction of a degree away from Earth. If the vehicle is tumbling, if a star tracker has failed, or if the onboard navigation estimate is wrong, the narrow beam may sweep across the sky without lingering on the receiving station long enough for the signal to be acquired. Engineers often provide lower-gain antennas with wider coverage for emergencies, but their broader beams deliver much less power in any one direction, reducing the data rate and limiting the range at which useful communication can be sustained. The lost crew might therefore begin not with a detailed video report, but with the simplest possible carrier, a steady radio tone that says almost nothing except that the spacecraft is still present. Such a tone can be detected at lower signal levels than a complex stream of data because the receiving system can integrate its energy over time, searching a narrow band of frequencies until a pattern rises above the noise. Deep space antennas do not hear a distant spacecraft in the ordinary sense. They infer it statistically from voltages so faint that thermal motion in electronics, natural radio emission from the sky, interference from Earth, and radiation from nearby astronomical objects may all be stronger at any instant. The meaningful quantity is the ratio of signal energy to noise, improved through larger receiving dishes, colder low-noise amplifiers, longer integration, narrower bandwidth, precise frequency prediction, and coding schemes that allow corrupted data to be reconstructed. This is why the giant parabolic antennas of NASA's Deep Space Network are distributed near Goldstone in California, Madrid in Spain, and Canberra in Australia. Their separation by roughly a third of Earth's circumference allows at least one complex to face a given region of interplanetary space as the planet rotates, creating the possibility of nearly continuous coverage when mission schedules and geometry permit. The largest antennas are about 70 meters across, not because radio waves from a spacecraft arrive as a broad physical object that must fit inside the dish, but because a larger collecting area intercepts more of the weak wavefront and focuses it toward a sensitive receiver. Multiple antennas can also be arrayed, combining their observations so that they behave in some respects like a larger instrument, a method used when a signal has become too faint for a single dish to recover efficiently. Yet even such a network cannot escape the communication budget imposed by physics. As distance increases and received energy decreases, the spacecraft may have to lower its data rate. A rich stream of images can become a slow flow of engineering numbers. Then, a few bits reporting battery voltage, temperature, and attitude. And finally, only a carrier whose continued presence confirms survival. Lowering the rate allows more energy to be devoted to each bit, making the information more resistant to noise. Error-correcting codes add carefully designed redundancy, allowing a receiver to detect and repair many mistakes without asking the spacecraft to retransmit every damaged fragment. This apparent inefficiency is one of the quiet triumphs of information theory. Extra symbols can reduce the total cost of communication because they preserve meaning across a channel where many individual bits arrive uncertain. Interleaving can spread a burst of interference across multiple code words, while repeated transmissions and long integrations exchange speed for reliability. The ultimate rate is governed not by distance alone, but by the complete link budget, transmitter power, antenna gain, frequency, spacecraft orientation, atmospheric attenuation, receiver sensitivity, background noise, coding performance, and the time available to observe. Higher frequencies can support narrower beams and potentially greater bandwidth, but they also demand more precise pointing and may be affected differently by weather in Earth's atmosphere. The communication beam must pass through the troposphere before reaching a ground antenna, where water vapor and atmospheric conditions can introduce attenuation and phase disturbances, particularly at higher radio frequencies. Solar plasma creates another kind of uncertainty. When the spacecraft appears close to the Sun in Earth's sky, radio waves pass through the turbulent, electrically charged solar corona, which can delay, scatter, and distort the signal. During solar conjunction, when Earth, the Sun, and the spacecraft approach alignment, reliable communication may become difficult enough that missions reduce commanding and place vehicles into carefully prepared autonomous modes. If the Sun lies directly between Earth and the lost ship, the problem is not that the solar surface forms a permanent wall, but that the powerful radio environment and intervening plasma can overwhelm or corrupt the faint spacecraft link. A planet can cause a more complete interruption by physically occulting the spacecraft, placing solid matter between transmitter and receiver. The ship might remain fully operational behind Jupiter or another world, while Earth hears nothing until orbital motion restores the line of sight. Silence is therefore an ambiguous observation. It could mean that electrical power has failed, but it could also mean that the antenna is mispointed, the transmitter is operating at an unexpected frequency, the vehicle has entered safe mode, the signal is temporarily blocked, the data rate is too high for current conditions, or Earth is listening at the wrong time and place. A spacecraft in safe mode often shuts down non-essential equipment, stabilizes its orientation, seeks the sun for power, and transmits a simple status signal, prioritizing survival over science. If navigation has failed, however, even finding Earth may be difficult. The direction to Earth changes continuously as both the planet and spacecraft move, so the antenna must be steered using an ephemeris and an estimated trajectory. A pointing error that seems tiny in angle can displace the beam by millions of miles at interplanetary distances. Once a signal is detected, it becomes more than a carrier of words. Its frequency and timing reveal motion. The Doppler effect shifts the received frequency when the spacecraft moves toward or away from the ground station, allowing navigators to estimate line-of-sight velocity with remarkable precision. A coherent transponder may receive an uplink based on a stable ground frequency and return a downlink at a known ratio, enabling accurate two-way Doppler measurements that reduce dependence on the spacecraft's own oscillator. Ranging signals embedded in the radio link can measure round-trip travel time and therefore distance, while repeated observations help reconstruct the trajectory. Communication and navigation are thus woven into the same faint thread. The act of hearing the ship also helps determine where it is and how it is moving. But the thread is never continuously available by default. Deep space networks support many missions, and antennas are scheduled according to mission needs, emergencies, maintenance, planetary encounters, and competing scientific priorities. A lost spacecraft transmitting outside an expected contact window might go unheard until operators direct an antenna toward the correct region and search across a plausible range of frequencies. Because the vehicle's motion shifts the carrier through Doppler effects, and its oscillator may have drifted, the search must explore both sky position and frequency, sometimes using open-loop recordings that preserve a wide band for later analysis. The weaker the signal, the longer the receiving system may need to integrate before distinguishing it confidently from random fluctuations. This introduces a final, almost tender asymmetry into the distress call. The ship can send its message in a moment, but Earth may need hours of observation to realize that the message is there. By then, the spacecraft has traveled onward, perhaps hundreds of thousands of miles from the place where the call began. The answer eventually transmitted from Earth may be scientifically precise, filled with commands, frequencies, and calculated burn times, yet it too enters the darkness as an artifact of an earlier calculation. Pursuing a moving vessel, it cannot reach any faster than light. And so, the first call home would not truly end when the transmitter falls silent. It would continue crossing the solar system long after the crew had returned to their instruments, long after the cabin lights had dimmed for another artificial night, carrying their recorded voices through a vacuum that neither weakens from loneliness nor hurries out of compassion. Until, at last, an antenna on a rotating blue world gathers a nearly immeasurable portion of its energy and transforms that faint arrival into the knowledge that somewhere beyond the planets, the lost ship is still alive. Once the spacecraft's position has been estimated and its faint signal has begun the long journey toward Earth, another calculation quietly takes precedence over every map and every message. not how far away home is, but how long the small artificial world inside the hull can continue to support human life. The survival clock does not begin with one dramatic countdown displayed in red. It begins as several overlapping clocks, each moving at a different pace, each governed by a different substance or machine, and each capable of ending the mission before the others have expired. There is a clock for cabin pressure, one for oxygen, one for carbon dioxide removal, one for electrical power, one for water, one for food, one for thermal control, and one for the slow accumulation of failures that no checklist can predict perfectly. The true remaining lifetime of the crew is not the sum of these resources, nor even their average. It is determined by whichever essential system becomes unrecoverable first. A spacecraft could carry months of food and still become uninhabitable within hours if the cabin loses pressure. It could contain abundant oxygen and yet become dangerous because carbon dioxide is no longer being removed. It could retain air, water, and food, while a failure in thermal control causes electronics to overheat or water lines to freeze. Survival in deep space is therefore a problem of coupled systems, where the health of one machine changes the burden placed upon several others, and where every human breath is part of an engineering equation. The atmosphere inside the cabin appears calm, but it is continuously being transformed. Each person consumes oxygen and releases carbon dioxide, water vapor, heat, and trace compounds through respiration, perspiration, cooking, hygiene, and ordinary metabolism. Oxygen is usually the resource people imagine first, yet carbon dioxide may become the more immediate concern, because even modest increases can produce headache, fatigue, impaired concentration, disturbed sleep, and reduced decision-making ability, long before oxygen is fully depleted. In a sealed volume, exhaled carbon dioxide accumulates unless it is captured by chemical absorbents, molecular sieves, regenerative scrubbers, or another active removal system. The Apollo 13 accident offered a famous demonstration of this principle when the crew possessed oxygen but faced rising carbon dioxide because square filter cartridges from one module could not initially fit the round receptacles in another. The improvised adapter that followed was not merely an inventive repair, it revealed a fundamental truth of closed habitats. Air is not made safe simply because it contains oxygen. Its composition must be continually managed. The approximate partial pressure of each gas matters more than the percentage alone, because biological effects depend on how many molecules are available within a given volume and pressure. If the cabin pressure falls while the oxygen fraction remains unchanged, the amount of oxygen reaching the lungs also falls. A spacecraft may use an Earth-like mixture of oxygen and nitrogen at moderate pressure, or a different pressure and composition chosen for mass, fire safety, structural design, and operational needs. But every architecture must keep oxygen partial pressure within a survivable range while controlling carbon dioxide and trace contaminants. Pressure itself is another silent clock. The hull does not need to split dramatically for danger to begin. A small puncture, damaged seal, faulty valve, or leaking hatch can release gas steadily into vacuum, and the rate depends on the size and geometry of the opening, the cabin pressure, gas temperature, and whether the flow becomes choked as it passes through the leak. Sensors may detect a falling pressure trend, but locating a tiny leak inside a complex vehicle can be difficult. because sound behaves differently in the enclosed structure. And air currents may carry clues away from the source. The crew might isolate modules, close hatches, monitor pressure changes, and use handheld detectors to narrow the search, sacrificing habitable volume to preserve the remaining atmosphere. Every compartment sealed off reduces the amount of space that must be maintained. Yet, it may also remove access to equipment, storage, or cooling loops located behind the closed hatch. Oxygen reserves may come from compressed gas, cryogenic storage, chemical generators, or electrolysis systems that split water into oxygen and hydrogen. Electrolysis can reduce dependence on stored oxygen, but it requires electrical power, functioning pumps, clean water, separators, sensors, and methods for managing the hydrogen produced. This is why life support capacity cannot be measured by a single tank gauge. A system that appears regenerative is never entirely independent. It remains attached to electricity, spare parts, control software, filters, and the physical condition of pipes and membranes. Water presents a similar illusion of circularity. Modern spacecraft can recover moisture from cabin air and process wastewater, including humidity condensate and, in some systems, urine, returning much of it to useful form through filtration, distillation, catalytic oxidation, and chemical treatment. Yet no practical spacecraft water cycle is perfectly closed. Water is lost in waste products, maintenance procedures, leaks, discarded filters, surface films, food preparation, and chemical reactions. Recovery systems also consume power and contain components that foul, corrode, clog, or require replacement. The crew's minimum daily water need can be reduced by rationing, but extreme conservation has consequences for hydration, hygiene, kidney function, food preparation, and the ability to clean equipment. The body can survive far longer without food than without water, but malnutrition is not a distant concern when the mission stretches from days into months. Stored food provides energy, protein, essential fats, vitamins, and minerals, yet its nutritional quality changes over time. Some vitamins degrade during long storage. Textures deteriorate, packaging may fail, and appetite can decline under stress or altered taste perception. Severe caloric restriction saves supplies, but weakens muscle, impairs immune function, reduces cognitive performance, and makes repairs more physically demanding. The crew is not merely waiting to be rescued. They must remain capable of operating a complex vehicle, which means survival cannot be defined as the lowest biological threshold at which a person remains alive. It must include the ability to think clearly, move effectively, and respond to new failures. Electrical power binds nearly every part of this system together. Fans must circulate air so carbon dioxide does not collect in stagnant pockets. Pumps must move coolant and water. Valves must open. Sensors must measure pressure, temperature, humidity, and gas composition. Computers must regulate the habitat, and heaters must prevent critical components from becoming too cold. If power generation falls, the crew may shut down experiments, lights, computers, communication systems, and unused modules, preserving only the loads required for life support and guidance. Solar arrays produce energy as long as they receive adequate sunlight and remain properly oriented. but their output generally decreases with increasing distance from the sun according to the weakening solar flux, while dust, radiation damage, micrometeoroid impacts, temperature cycles, and material degradation can slowly reduce performance. Batteries can bridge periods of darkness or high demand, yet they store rather than create energy, and repeated charge cycles gradually reduce their capacity. Radioisotope power systems operate independently of sunlight and decline predictably as their radioactive fuel decays and thermoelectric components age. But they are usually designed for robotic spacecraft and may not provide the enormous electrical load required by a large, crewed habitat. Choosing what to power becomes a form of triage. Communication may be reduced to brief transmissions. Cabin temperature may be allowed to drift within a wider range. Redundant computers may be turned off. Portions of the vehicle may be abandoned and allowed to cool, concentrating the crew into a smaller, protected volume where less air must be circulated and less heat must be supplied. Yet cold is only half of the thermal problem. A crewed spacecraft continuously generates waste heat from human metabolism and electrical equipment, and vacuum provides no surrounding air to carry that heat away by convection. The vehicle must transport heat through internal fluid loops and radiate it into space from external surfaces. If a radiator is damaged, shaded incorrectly, contaminated, or isolated by a failed pump, the spacecraft may overheat even while drifting through a region commonly described as freezing. Temperature in space is not a simple property of emptiness. It is the result of the balance between absorbed radiation, internal heat production, reflected sunlight, emitted infrared energy, surface properties, and orientation. A dark surface facing the sun may become intensely hot, while a shaded component nearby becomes dangerously cold. Thermal design therefore depends on coatings, insulation, heaters, louvers, heat pipes, fluid loops, and radiators working together. Turning the spacecraft to improve antenna alignment may alter solar heating. Rotating to illuminate a solar array may expose a radiator to sunlight. Closing a module to conserve air may interrupt coolant circulation through equipment still needed elsewhere. Every action rearranges the energy balance. Fire introduces a different kind of coupling because it consumes oxygen, produces heat, smoke, carbon monoxide, carbon dioxide, corrosive compounds, and particles that can enter electronics and filters. In microgravity, flames do not rise into the familiar teardrop shape created by buoyant convection on Earth. Without gravity-driven flow, combustion products remain near the flame until ventilation moves them, producing shapes and behaviors that depend strongly on airflow. Extinguishing the visible flame may not end the danger if heated materials continue to smolder behind panels or toxic residues circulate through the cabin. Fire suppression agents must stop combustion without making the atmosphere unbreathable or damaging critical equipment, and afterward, the life support system must remove contaminants from an air supply that cannot simply be replaced by opening a window. Redundancy offers protection, but only when failures are genuinely independent. Two carbon dioxide scrubbers connected to the same electrical bus may both be lost when that bus fails. Three computers running identical software may all respond incorrectly to the same corrupted input. Separate oxygen tanks may share a common line or regulator. Engineers study common cause failures precisely because duplicated hardware can create a comforting appearance of safety while preserving one hidden point of vulnerability. Long-duration survival demands dissimilar redundancy, physical separation, manual bypasses, repairable components, spare parts, and a crew trained to understand systems well enough to improvise outside normal procedures. Even then, maintenance creates its own countdown. Filters fill, seals harden, lubricants migrate, microbes grow in moist surfaces, sensors drift, pumps wear, and radiation slowly damages electronics. The longer the ship remains lost, the more survival depends not on the original design alone, but on whether the crew can diagnose unfamiliar combinations of degradation using limited tools and finite materials. A failed fan might be replaced with a spare, repaired with parts from an unused system, or compensated for by changing airflow paths. But every improvised repair spends time, energy, and hardware that may later be needed elsewhere. The survival clock is therefore not fixed at the moment of the accident. It can be lengthened by intelligent rationing, isolation, repair, and lower metabolic demand, or shortened by panic, unnecessary power use, contamination, and poorly timed maneuvers. Mission Control may calculate optimistic and conservative timelines, but both remain conditional because the spacecraft is a living network of interacting uncertainties. A pressure leak may remain stable for weeks or suddenly widen under thermal cycling. A battery may retain capacity longer than expected or fail after one damaged cell overheats. A water processor may be restored with a cleaning procedure, while a minor valve fault may prove inaccessible behind the hull. The crew would gradually learn to listen to the vehicle as sailors once listened to wooden ships. The vibration of a pump, the changing pitch of a fan, the warmth of a panel, the unusual rhythm of a valve, each sensation becoming a fragment of medical information about the artificial organism surrounding them. Beyond the hull, the universe remains almost perfectly silent, but inside, life is a continuous mechanical conversation. Air moves because fans move it. Water returns because membranes separate it. Heat leaves because radiators face the darkness. Every breath is borrowed from a machine that must perform again, and then once more through the artificial night. The final limit will not necessarily arrive when every resource is gone. It will arrive when the first indispensable process can no longer be sustained. When no remaining repair, reserve, bypass, or reduction in demand can keep the habitat within the narrow physical conditions the human body requires. Until that moment, however, the countdown is not simply a march toward failure. It is a changing field of possibilities, and every careful decision can purchase another hour of pressure, another day of clean air, another cycle of warmth and water, while the lost spacecraft continues carrying its fragile interior world through a darkness where survival is measured not by distance traveled, but by how long matter, energy, machinery, and human judgment can remain in balance. The human body would begin changing almost as soon as the lost spacecraft settled into its long, unpowered drift. not because gravity had vanished from the universe, but because the crew and the vehicle would be falling together through the same gravitational field, leaving almost no steady force pressing feet against a floor, blood toward the legs, or bones against the weight they evolved to carry. Within minutes, fluids that gravity normally pools in the lower body would begin migrating toward the chest and head, making the face appear slightly fuller, the nasal passages feel congested, and the legs look thinner. A redistribution sometimes described with the plain but accurate phrase, puffy face and bird legs. Sensors in the heart, neck, kidneys, and blood vessels interpret the increased central fluid volume as an excess, and the body responds by reducing plasma volume through changes in thirst, hormones, and urine production. What begins as an adaptation to weightlessness can later become a weakness, because the circulatory system is gradually retuned for a world where it no longer has to push blood upward against gravity. The heart continues working, but its mechanical demands change, and over time, cardiac filling, vascular control, and aerobic capacity may be altered. If the crew eventually enters a gravitational field again, standing can suddenly become difficult. Blood may fall toward the legs, pressure near the brain may drop, and dizziness or fainting can follow because the system has forgotten part of the work it once performed automatically. Before those slower changes unfold, the nervous system must solve a more immediate puzzle. On Earth, the brain combines signals from the eyes, skin, joints, and vestibular organs of the inner ear to decide which way is up and whether the body is moving. In microgravity, the otolith organs no longer receive the familiar, persistent pull that distinguishes head up from head down, while the eyes may report motion that the inner ear does not interpret in the usual way. The conflict can produce space motion sickness and disorientation during the first days, although many astronauts adapt as the brain learns to reinterpret the new sensory pattern. This is not the restoration of an old map, but the construction of a new one, which is why landing on the Moon, Mars, or Earth demands another period of recalibration. Meanwhile, the musculoskeletal system begins obeying a harsh economy. Tissue that is no longer loaded is tissue the body becomes reluctant to maintain. On Earth, the calf muscles, quadriceps, spinal muscles, hips, and trunk perform thousands of small contractions simply to keep a person upright. In a drifting spacecraft, translation requires little more than a push from a fingertip, so the anti-gravity muscles receive fewer signals to preserve their size and strength. Protein synthesis and breakdown shift. Muscle fibers can shrink. Endurance declines, and the loss is not perfectly uniform across the body. Exercise devices that create resistance are therefore not optional luxuries, but artificial substitutes for gravity, asking the muscles to pull against loads even though the spacecraft provides no weight. Bone follows a related but slower process. Living bone is continually remodeled by cells that remove old tissue and cells that build new tissue, and mechanical loading helps regulate the balance between them. When weight-bearing bones are unloaded, resorption may exceed formation, releasing calcium and other minerals into the bloodstream. The resulting decline is strongest in regions such as the pelvis, spine, and legs, while the elevated urinary calcium can contribute to kidney stone risk. In long-duration missions, careful exercise, nutrition, medical screening, and sometimes additional countermeasures reduce these changes, but they do not make the body behave exactly as it does on Earth. The underlying lesson is almost philosophical in its simplicity. The skeleton is not a fixed frame carried unchanged through life. It is a responsive archive of the forces the body has recently experienced. Even the spine participates in the transformation. With less compression between the vertebrae, the spinal column may lengthen slightly, and crew members can become temporarily taller. Yet the change can be accompanied by back discomfort and altered loading of connective tissues. The blood itself also adapts. Soon after entering microgravity, the reduction in plasma volume changes the concentration of circulating cells, and over longer periods, red blood cell mass may decrease through a combination of altered production and destruction, a phenomenon sometimes called space anemia. Recent research continues to refine the mechanisms and their significance for very long missions, especially when nutrition, radiation, inflammation, and individual biology interact. The immune system does not simply switch off, but aspects of immune regulation can change, including the behavior of certain white blood cells, inflammatory signaling, and the reactivation of latent viruses already carried in the body. These findings vary among individuals and are difficult to assign to one cause because spaceflight combines microgravity, disrupted sleep, confinement, stress, radiation, and altered diet. A lost crew would therefore face not one isolated biological variable, but a system of pressures that overlap, sometimes amplifying one another. Sleep would become one of the most important stabilizers. Far from a natural sunrise and sunset, the body's circadian timing would depend on scheduled light, darkness, meals, activity, and disciplined routines. If cabin lighting is poorly timed, alarms interrupt rest, anxiety delays sleep, or work shifts drift across the artificial day, fatigue can accumulate and weaken reaction time, judgment, immune regulation, and emotional resilience. In a crisis, this matters because the body may remain technically alive while losing the precision required to repair the machine that keeps it alive. The eyes reveal another, still incompletely understood adaptation. During long exposure to microgravity, some astronauts develop a group of findings known as spaceflight-associated neuroocular syndrome, which can include flattening of the back of the eyeball, swelling near the optic disc, folds in tissues at the rear of the eye, and changes in focusing ability. The leading explanations involve headward fluid shifts and altered pressure relationships among the brain, cerebrospinal fluid, blood vessels, and eye, but the full mechanism has not been settled, and individual susceptibility differs. That uncertainty becomes especially important in deep space, where a crew may need sharp vision for delicate repairs and autonomous medical care long after rapid return is impossible. Outside Earth's protective atmosphere and much of its magnetic shielding, radiation adds a hazard that microgravity alone cannot explain. Solar particle events can deliver elevated doses over hours or days, often dominated by energetic protons accelerated during solar activity, while galactic cosmic rays arrive persistently from beyond the solar system and include high-energy atomic nuclei capable of producing complex tracks of ionization through tissue and generating secondary particles when they strike the spacecraft. Their effects depend on particle type, energy, dose, shielding, tissue sensitivity, genetics, and mission duration. Radiation can damage DNA directly or indirectly through reactive molecules, and cells may repair that damage correctly, misrepair it, enter permanent arrest, or die. Long-term concerns include cancer, cardiovascular and degenerative effects, and possible consequences for the central nervous system, although some deep space risks remain difficult to quantify because humans have not yet completed multi-year voyages far beyond low Earth orbit. Shielding can reduce exposure, particularly from mini-solar particles, but high-energy cosmic rays are difficult to stop completely, and adding material can sometimes create cascades of secondary radiation. So protection is a problem of composition, geometry, forecasting, mission timing, and shelter design, rather than simply building the thickest wall possible. A compact storm shelter surrounded by water, food, equipment, or hydrogen-rich materials could offer improved protection during a solar event. Yet the chronic background of galactic radiation would continue to pass through the journey. The body would respond through repair, adaptation, inflammation, and accumulated injury, not through one visible moment of transformation. This is also why cinematic ideas about exposure to vacuum are so misleading. If the cabin lost pressure, a person would not explode, freeze instantly, or become a rigid statue in a single breath. The urgent problem would be oxygen deprivation, accompanied by the physical effects of decompression and the expansion of gases, and consciousness would likely be lost rapidly unless pressure and oxygen were restored. As long as the cabin remained sealed, however, the more likely story would be gradual and strangely orderly. The face would swell a little, the legs would surrender some of their volume, muscles would answer the absence of load, bones would revise their architecture, the heart and vessels would learn a new distribution of blood, the inner ear would stop insisting on a permanent down, the eyes might change their shape, sleep would become an engineered rhythm, and every cell would continue negotiating with radiation and time. None of these changes means that the human body is fragile in a simple sense. On the contrary, they reveal an organism of extraordinary flexibility, continually rebuilding itself to match the environment it believes will continue. The danger is that adaptation has no knowledge of the future. A body optimized for floating may be poorly prepared to land, climb, repair a heavy mechanism under gravity, or survive the next transition. And so, aboard the lost spacecraft, survival would depend not only on keeping the crew alive tonight, but on preserving enough muscle, bone, circulation, vision, sleep, and neurological function for whatever physical demand waits at the end of the silence. Because the body does not merely travel through deep space as a passenger. Slowly, cell by cell, it becomes a record of having been there. At first, the silence would not feel infinite at all. It would be filled with the ordinary sounds of machinery, the soft breath of ventilation fans, the intermittent click of relays, the faint movement of coolant behind the walls, and the private noises of the human body that are usually concealed beneath the wider music of Earth. Yet as the lost spacecraft moved farther from any immediate possibility of rescue, the mind would begin to recognize that this quiet was not simply the absence of sound, but the absence of response, a condition in which every question sent home might require hours to arrive. Every answer would return from an earlier version of reality, and no voice could could interrupt the present moment quickly enough to share its weight. Human cognition evolved in environments dense with feedback. A face changes when we speak. Weather shifts across a horizon. Footsteps reveal another person approaching, and even solitude on Earth contains indirect evidence of civilization through distant traffic, electric light, birds, wind, and the expectation that help exists somewhere beyond the door. Inside a drifting spacecraft, that web of reassurance becomes thin. The crew may still exchange messages with Earth, but increasing communication delay transforms conversation into correspondence, and the emotional effect is deeper than simple inconvenience. A person reporting fear cannot receive immediate reassurance. A physician on Earth may answer a medical question only after the patient's condition has changed. Mission controllers can offer guidance, but the crew must act before knowing whether their judgment will be confirmed. This reduction in external feedback increases what psychologists call perceived autonomy and perceived responsibility, two conditions that can strengthen confidence when a person feels prepared, yet can intensify stress when every decision appears irreversible. The mind does not respond to isolation in one universal way. Individual temperament, training, group trust, sleep quality, workload, habitat design, mission meaning, privacy, and the degree of control over events all influence the outcome. And findings from polar stations, submarines, orbital missions, simulated Mars habitats, and other confined environments suggest patterns rather than a single inevitable psychological path. One of the earliest pressures would be sustained uncertainty. A known danger can often be divided into tasks, schedules, and measurable thresholds. But an uncertain danger requires the brain to maintain several incompatible futures at once. The navigation system may recover or fail permanently. A signal may be heard or remain unnoticed. Life support may last months under ideal conditions, or far less if a hidden component fails. The nervous system repeatedly updates these possibilities, and because no final answer arrives, it may remain in a prolonged state of vigilance. Stress hormones, such as cortisol and catecholamines, are useful during acute emergencies, mobilizing energy and sharpening immediate responses. But chronic activation can disturb sleep, alter immune regulation, narrow attention, and increase irritability. The danger is not that the crew would remain visibly panicked for weeks. More often, prolonged stress can become quiet, settling into shortened tempers, reduced cognitive flexibility, repetitive checking, emotional withdrawal, or an exaggerated need to control small details because the largest facts remain uncontrollable. The spacecraft's sensory environment would intensify this process through monotony. Human attention is drawn naturally toward change, yet the cabin presents the same panels, the same storage bags, the same narrow passageways, and the same carefully manufactured light each day. Without new sensory landmarks, one period of wakefulness begins to resemble another. Studies of isolated groups have shown that monotony can reduce alertness and make time feel both slow and strangely indistinct, although the experience varies widely. The mind may begin to measure existence through maintenance cycles rather than mornings. Filter inspection, communication window, exercise period, meal, sleep. This structure can feel restrictive, but it is psychologically protective because routine converts an unlimited future into a sequence of finite actions. The crew does not have to endure the whole distance at once. They need only complete the next checklist, prepare the next transmission, and preserve the habitat through the next artificial night. Circadian rhythm becomes central to this stability. On Earth, the suprachiasmatic nucleus in the brain helps coordinate daily cycles of alertness, temperature, hormone release, and sleep, using light as its strongest timing signal. In deep space, natural illumination may be constant, weak, irregular, or operationally irrelevant. So carefully timed artificial light must provide the biological distinction between day and night. Blue-enriched light during the scheduled waking period can promote alertness, while dimmer and warmer light before sleep can support melatonin release. But lighting alone cannot overcome anxiety, equipment noise, emergency alarms, uncomfortable temperature, or shifting work demands. Sleep loss then feeds back into the crisis. Even modest restriction can weaken working memory, slow reaction time, impair emotional regulation, and increase the likelihood of accepting the first plausible solution rather than evaluating alternatives. In a spacecraft, where one incorrect valve setting or navigation command may have consequences that cannot be reversed, fatigue becomes not merely a private discomfort, but an engineering hazard. Carbon dioxide levels that remain below acute toxicity may still contribute to headache, sleep disruption, and reduced cognitive performance in some conditions, adding a physiological layer to what might otherwise be mistaken for a purely emotional decline. The crew would therefore monitor the mind, partly by monitoring the habitat, because cognition is inseparable from air quality, hydration, nutrition, radiation exposure, pain, medication, and the body's adaptation to microgravity. Time perception would also change. During repetitive days with few memorable events, long intervals can seem slow while they are occurring, yet compressed when recalled, because memory estimates duration partly from the number of distinct experiences stored within it. A tense wait for a signal may feel almost motionless, each minute watched closely, while several hours spent repairing a pump may vanish into concentrated action. This elasticity of time can become unsettling when no natural season, sunrise, or landscape confirms that life is moving forward. Calendars, mission logs, personal journals, recorded messages, and small rituals would provide evidence of continuity. Writing down observations does more than preserve technical history. It places events into sequence and prevents the mind from experiencing the crisis as one endless present. Privacy would be equally important, especially if more than one person were aboard. Confinement creates a paradox in which crew members depend intensely upon one another while possessing almost no ability to withdraw. Sounds carry through thin walls, schedules overlap, personal habits become visible, and minor disagreements can acquire disproportionate emotional force because there is no separate home to return to afterward. Research from isolated teams suggests that cohesion is supported not by the absence of conflict, but by clear roles, fair workload, reliable leadership, and methods for addressing tension before it becomes personalized. Under extreme uncertainty, groups may search for someone to blame, because causation feels easier to tolerate than randomness. A failed component may become associated with the crew member who last handled it, even when the true failure arose from material fatigue or design limitations. Effective teams would counter this tendency through procedural language, separating observations from accusations, and treating mistakes as information about the system. Yet, excessive harmony can also become dangerous if crew members suppress doubts to preserve peace. High reliability decision-making requires the freedom to challenge a plan, particularly when fatigue and urgency make authority feel comforting. The most resilient group would not be the one that never disagrees, but the one capable of disagreement without allowing it to fracture trust. Decision fatigue would gradually become another hidden cost. Every day might require choices about energy use, maintenance priorities, rationing, communications, exercise, medical risk, and whether to spend fuel correcting an uncertain trajectory. Each decision consumes attention, and when consequences are grave, even simple choices can become heavy. Procedures reduce that burden by establishing thresholds in advance. If pressure falls below a certain level, isolate a module. If battery capacity reaches a defined point, shut down non-essential loads. If a communication attempt fails, repeat the search according to a fixed sequence. Such rules do not eliminate judgment, but they prevent the crew from rebuilding every decision from the beginning while exhausted. Autonomous software may support this process by detecting anomalies and proposing actions, though reliance on automation introduces its own psychological tension. A crew that cannot understand why the system recommends a maneuver may hesitate to trust it, while a crew that trusts it unquestioningly may overlook corrupted data or an incorrect model. The relationship between human and machine becomes a form of shared cognition, each compensating for the other's weaknesses. Computers maintain precision and consistency, while humans interpret unfamiliar context, improvise with damaged equipment, and recognize when the assumptions beneath an algorithm no longer match reality. As days become weeks, emotional states might fluctuate rather than deteriorate in a straight line. Relief after repairing a system may be followed by exhaustion. A successful contact with Earth may restore hope, then deepen loneliness when the transmission ends. People sometimes report a third-quarter effect during long, isolated missions, a proposed pattern in which mood and morale worsen after the midpoint, when the novelty has disappeared, but the end still feels remote, although research does not show it uniformly across all settings. A lost mission has no reliable midpoint, making progress harder to perceive. The crew would need to create intermediate goals that are meaningful, even without certainty of rescue. Reduce power consumption by a measurable amount. Refine the orbit estimate. Restore one redundant system. Complete a medical assessment. Preserve physical conditioning for another week. These goals turn survival from passive waiting into skilled activity, and agency is one of the strongest protections against helplessness. Contact with Earth, however delayed, would remain psychologically valuable when it includes more than technical instructions. Recorded voices, familiar music, images of weather, and ordinary stories from home can reconnect the crew to a world larger than the emergency. Yet, such messages might also produce complex reactions, bringing comfort to one person and painful distance to another. Support would need to respect individual preference rather than assuming that constant reminders of home always help. The view outside could carry a similar dual meaning. For some, the stars might produce awe, a sense of belonging within a vast physical order that makes personal fear feel smaller. For others, the same view could emphasize vulnerability and distance. Awe itself is not simple happiness. It arises when perception encounters something too large for existing mental categories, forcing the mind to adjust its sense of scale. In deep space, that adjustment may become part of survival. The crew cannot make the universe intimate, but they can make their immediate environment understandable. They can name each sound, track each resource, divide each problem into actions, and preserve a daily rhythm within the larger timelessness. The silence outside remains immense, but the mind does not face it as an empty vessel. It carries memory, discipline, language, training, companionship, and the remarkable human ability to construct meaning from repetition. The deepest psychological danger would not necessarily be fear itself, because fear can focus attention and motivate care. It would be the gradual loss of structure, the moment when days cease to feel connected, decisions cease to feel consequential, and the future becomes too shapeless to imagine. Against that possibility, routine becomes a kind of gravity, pulling thought back toward the present. Conversation becomes atmosphere, carrying emotion between people, and each completed task becomes a small horizon drawn inside a place that has none. Far beyond the planets, where no immediate answer can return, and no sunrise arrives unless the lamps are commanded to create one, the human mind would survive by doing what it has always done in darkness: measuring time, sharing responsibility, telling the truth about danger, and building a livable world from whatever patterns remain. Outside the hull, the darkness would appear almost perfectly empty, and that appearance would be both truthful and misleading, because deep space contains so little matter that a human mind trained on oceans, storms, and landscapes struggles to recognize the kinds of danger that remain. There would be no wind pressing against the spacecraft, no rain striking the windows, and no surrounding air carrying away heat. Yet the absence of an environment does not mean the absence of physical influence. It means that every influence arrives by quieter routes: photons crossing the void, charged particles following magnetic fields, grains of dust moving at enormous relative speed, and tiny failures in material protection accumulating where no repair crew can easily reach them. The first misconception to abandon is that space itself is simply cold. Temperature is a property of matter and its internal energy, while the vacuum around the ship contains too few particles to behave like a frigid atmosphere. An object in space does not lose heat rapidly through contact with surrounding air, because there is almost no air to conduct or convect that heat away. Instead, the spacecraft exchanges energy mainly through radiation, absorbing sunlight and infrared emission from nearby bodies, while releasing its own thermal energy as infrared photons. Its temperature, therefore, depends on an energy balance rather than on a single number assigned to the surrounding darkness. A sunlit surface near Earth's orbit can become intensely hot, while a shaded surface only a short distance away may cool toward dangerously low temperatures. The relation is often approximated through the Stefan-Boltzmann law, in which radiated power grows with the fourth power of absolute temperature, meaning that a modest rise in temperature can greatly increase the rate at which a surface emits heat. The spacecraft's equilibrium temperature is shaped by solar intensity, surface area, orientation, reflectivity, emissivity, internal electrical loads, and the ability of thermal pathways to move heat toward radiators. A dark coating may absorb more solar energy than a reflective one, while a surface engineered to emit infrared efficiently can help remove waste heat. Layers of thin reflective insulation reduce radiative exchange between components. Heaters protect sensitive instruments, and fluid loops carry energy away from crowded machinery. But every element is designed around expected orientations and operating modes. A lost spacecraft that turns to point an antenna toward Earth may expose a radiator to direct sunlight, place a fuel line in prolonged shadow, or illuminate one side of the hull for far longer than its designers intended. Thermal danger is therefore geometric. It arises not because the universe is uniformly freezing, but because the vehicle can no longer maintain the carefully planned relationship between light, shadow, and heat. Beyond temperature, the most intuitive external threat is collision, although the objects involved are usually much smaller than cinema suggests. Interplanetary space contains dust grains, fragments from comets, particles released by asteroids, and occasional larger natural bodies, but the average density is extraordinarily low. The ship is not moving through a dense swarm. Most of the time, it crosses distances so vast that nothing visible comes near it. Yet collision energy depends strongly on relative velocity, with kinetic energy proportional to 1/2 the mass multiplied by the square of speed. Because speed is squared, a particle too small to notice on Earth can become significant when it strikes at several or tens of kilometers per second. At such hypervelocity, the impact does not resemble a pebble tapping metal. Pressures rise so quickly that part of the particle and part of the target can melt, vaporize, or form a rapidly expanding cloud of fragments. A grain may leave a crater, damage a sensor, puncture a thin radiator tube, degrade an optical surface, or weaken an outer layer without producing an immediately obvious emergency. The threat is managed through probability, material design, and shielding, rather than through the hope of seeing objects in time to dodge them. For many crewed vehicles, vulnerable regions can be protected by variations of the Whipple shield, a concept developed during the early space age in which a thin outer bumper is placed some distance ahead of the main pressure wall. When a small, high-speed particle strikes the bumper, it breaks apart and spreads into a wider cloud, allowing the deeper wall to absorb the remaining energy over a larger area. More elaborate shields use multiple layers, fabrics, ceramics, metals, and spacing selected for expected particle sizes and velocities. No practical shield makes a spacecraft invulnerable because mass is expensive to launch and sufficiently large impactors can overwhelm any reasonable protection. But engineering can make the most probable small impacts survivable. Near Earth, artificial orbital debris adds a serious hazard, including fragments from old spacecraft, rocket stages, accidental collisions, and destructive events. But this population is concentrated largely within commonly used Earth orbits. Farther into interplanetary space, the danger from human-made debris falls sharply, leaving natural micrometeoroids as the more relevant collision environment. The distinction matters because deep space is not a junk-filled ocean extending uniformly between planets. Its emptiness is real, and that emptiness makes a random encounter with a large asteroid, rogue planet, or black hole extraordinarily improbable. Planets and stars are enormous compared with a spacecraft, but the spaces between them are vastly larger still. Even the asteroid belt is mostly open distance, and spacecraft have crossed it many times without weaving through a crowded field of rocks. A lost vessel would not be expected to stumble accidentally into a hidden planet. Its more credible threats would remain small particles, uncertain trajectories near known bodies, and failures produced by long exposure. Dust becomes a more serious theoretical obstacle for vehicles traveling at a substantial fraction of the speed of light, because the kinetic energy of even tiny grains would become extreme, and ordinary approximations would eventually require relativistic treatment. For the far slower speeds of present-day crewed spacecraft, dust is dangerous locally, but does not form an impenetrable barrier to travel. The emptiness between particles also means that drag is almost absent. Neutral atoms, ions, and dust exert some resistance, but under ordinary interplanetary conditions, the effect on a conventional spacecraft is usually far too weak to slow it meaningfully over a human lifetime. The ship would not be cushioned into rest. It would continue carrying every small defect forward, accumulating damage without receiving the compensating protection of a surrounding atmosphere. Charged particles create another class of hazard that may leave no visible mark on the exterior. The solar wind is a thin plasma flowing outward from the sun, composed mainly of protons and electrons embedded in the interplanetary magnetic field. A spacecraft exposed to sunlight, plasma, and energetic particles can gain or lose electrical charge depending on how electrons and ions interact with its surfaces and how photoelectrons are emitted. Different materials or shaded regions may charge to different electrical potentials, and if the difference becomes large enough, an electrostatic discharge can occur. Such discharges may interfere with instruments, damage electronics, corrupt data, or trigger false commands. Designers reduce these risks through conductive surfaces, grounding paths, shielding, component selection, and careful control of electrical interfaces. Yet a damaged or aging vehicle may become more vulnerable as coatings degrade and connections loosen. Solar activity can intensify the particle environment. Coronal mass ejections and solar energetic particle events can disturb magnetic fields, increase radiation levels, and alter spacecraft charging conditions. Although the severity at a particular spacecraft depends on the event's direction, energy distribution, timing, and distance from the sun. Farther outward, the intensity of sunlight and many solar influences declines, but the background of galactic cosmic rays remains, bringing high-energy nuclei from outside the solar system. Their biological consequences belong to the crew's medical story, yet they also affect hardware. A single energetic particle passing through a semiconductor may deposit enough charge to flip a memory bit, disturb a processor, latch a circuit into a dangerous state, or damage a component permanently. These single event effects can be mitigated through radiation-hardened electronics, error-correcting memory, redundant computers, current limiting, software checks, and periodic resets. The spacecraft may continue functioning after countless particle passages, then respond strangely to one rare interaction in a critical location. This is why deep space reliability depends less on preventing every error than on detecting, isolating, and recovering from errors that cannot be prevented completely. Materials themselves also change under prolonged exposure. Ultraviolet light can alter polymers and coatings. Radiation can embrittle or discolor certain substances. Repeated heating and cooling can fatigue joints, and vacuum can encourage volatile compounds to escape from materials in a process known as outgassing. Released molecules may later condense on cold optics, radiators, or sensors, degrading performance far from the component that produced them. Lubrication is difficult because ordinary oils may evaporate, migrate, or behave poorly across extreme temperatures, so moving mechanisms rely on specialized lubricants, dry films, bearings, and carefully selected materials. Even two clean metal surfaces can adhere under certain vacuum conditions if protective films are absent, a phenomenon associated with cold welding, although real spacecraft design reduces the likelihood through surface treatments, material pairing, and contamination control. None of these hazards resembles a monster waiting beyond the window. They are interactions among surfaces, particles, energy, and time. Their seriousness depends on exposure duration and on whether the spacecraft can continue adapting. A micrometeoroid strike that would be a minor maintenance issue near Earth may become mission-defining when no replacement radiator panel exists. A corrupted memory word that would normally be corrected by ground control may become more consequential when communication requires hours. A thermal imbalance that begins as a small temperature drift may damage a battery, which reduces power, which weakens heating, which allows another system to fall outside its operating range. Deep space danger often propagates through chains rather than arriving as a single overwhelming event. The rare, spectacular possibilities, an unseen black hole, a collision with a wandering world, a sudden encounter with a dense cloud, draw attention because they are easy to imagine, yet current astronomical knowledge suggests that their probability along an ordinary spacecraft trajectory would be extremely low. Black holes do not roam invisibly through every empty region, and their gravity does not pull distant objects with a mysterious force greater than that of any other mass of the same size. A stellar mass black hole would need to pass extraordinarily close before producing an immediate threat, and such encounters are not expected to define realistic mission risk. The more probable adversaries are familiar to engineering: temperature, radiation, electrical discharge, material fatigue, contamination, software error, and small impacts occurring in unfortunate places. The darkness is dangerous not because it is crowded, but because it offers no forgiving medium around the spacecraft and no easy route for repair. Every protective layer must be carried from home. Every radiator, cable, seal, and circuit must continue doing its work while sunlight shifts, particles arrive without warning, and the vessel travels through distances too large for rescue to be immediate. Outside the window, almost nothing moves visibly. The stars remain clear, the blackness remains undisturbed, and the hull may receive no noticeable impact for months. Yet the apparent stillness conceals a continuous exchange of energy and matter, so faint that only instruments can perceive it, and so persistent that the spacecraft's survival depends on respecting it. Deep space does not need to strike with violence. It can simply expose the ship, hour after hour, to a universe in which the smallest forces are granted enough time to become important. If Earth is going to find and rescue a spacecraft lost in deep space, the search cannot begin with a telescope sweeping randomly across the stars. Because the sky is too large, the target is too small, and the ship is already moving through a geometry that changes with every passing second. Instead, the rescue begins with the last moment of certainty, the final time at which navigators knew the spacecraft's position, velocity, orientation, engine activity, and clock state well enough to predict what should happen next. From that last reliable state, computers propagate thousands or millions of possible trajectories forward through the gravitational fields of the sun, planets, moons, and any other bodies important to the local path, while also allowing for uncertain forces such as a poorly measured thruster firing, a slow gas leak, radiation pressure, or an accidental change in attitude. The result is not one bright line through space, but a widening cloud of possibilities, often represented mathematically through a covariance matrix, confidence region, or collection of simulated particles, each one describing a slightly different future consistent with the imperfect evidence. A tiny uncertainty in velocity becomes especially cruel because position error grows with time. A difference of 1 meter per second becomes more than 80 kilometers after a day, thousands of kilometers after a month, and a much larger separation over longer periods, while gravity bends each possible path in a slightly different way. The search region may therefore stretch into a long, curved tube through space, narrow in some directions and immense in others. And Earth must determine not only where the spacecraft might be now, but where it will be when a receiving antenna, telescope, or rescue vehicle is finally able to look. Deep space navigation normally uses radio ranging, Doppler measurements, interferometric direction finding, and optical observations to estimate a spacecraft's trajectory, with NASA's Deep Space Network measuring signal timing and frequency shifts to infer distance and motion. If the lost ship is still transmitting, even a simple beacon would transform the problem. A radio signal contains a pattern that can be distinguished from the natural sky, and once large antennas detect it, its Doppler shift reveals part of the spacecraft's velocity along the line of sight, while coded ranging signals can estimate distance. Measurements repeated as Earth rotates and moves around the Sun change the observing geometry, gradually constraining directions that one observation alone cannot resolve. Very long baseline techniques can compare the signal's arrival at widely separated antennas, providing precise angular information against distant radio sources such as quasars. The ship's own transmission may be extraordinarily weak by the time it reaches Earth, but the receiving system can search across expected frequencies, combine observations over long intervals, and use the predicted motion of the target to separate a drifting carrier from random noise. The Deep Space Network exists precisely to communicate with and track distant interplanetary spacecraft through giant antennas located around the world. Yet even such sensitivity cannot guarantee detection when the beam is pointed elsewhere. The transmitter has failed, the antenna orientation is unknown, or the frequency has drifted beyond the searched range. Without a beacon, the spacecraft becomes far more difficult to find, because it must be detected through reflected sunlight or its own thermal emission. A human spacecraft might be physically large, yet at interplanetary distances, its angular size would be far below the resolving power of most telescopes, reducing it to a faint point whose brightness changes with distance, surface reflectivity, orientation, and illumination. It could be hidden in the glare near the sun, blended with background stars, or moving too slowly across the sky to be recognized during a short observation. Astronomers would need to image the predicted uncertainty region repeatedly and search for points that shift in a manner consistent with a possible spacecraft trajectory, a computational task resembling the recovery of a faint asteroid, though the spacecraft's brightness and motion might be less predictable because its attitude could be changing. Infrared observatories might search for waste heat from operating electronics, life support machinery, and warm surfaces. But thermal radiation also weakens with distance, and its apparent temperature depends on the vehicle's orientation, radiator design, power state, and surrounding background. A spacecraft conserving energy could become harder to see at the very moment its survival depends most urgently on being found. Radar would offer little comfort at truly deep space distances. A radar signal must travel outward, illuminate the target, scatter from its small surface, and send only a tiny fraction of its energy back toward Earth, so the received echo declines severely with range, commonly approximated by an inverse fourth power dependence in simple radar equations. Powerful planetary radars can study some asteroids and planets, but searching blindly for a spacecraft across a vast uncertainty volume would generally be far more demanding than receiving a beacon transmitted directly from the vehicle. The first condition for rescue is therefore knowledge. The uncertainty must be narrowed enough that Earth can predict a future meeting point rather than chase a fading object through an expanding region. Yet finding the ship is only the beginning, because rescue in space is not accomplished by arriving near the same coordinates. Two vehicles can pass through exactly the same location minutes apart and never see each other, or occupy nearby positions while moving in different directions at several kilometers per second. A true rescue requires rendezvous, which means bringing the rescue craft to the same position at the same time with a sufficiently small relative velocity to permit approach, docking, transfer, or another controlled form of contact. The distinction between interception and rendezvous is fundamental. An interceptor may cross the target's path at high speed, useful for an impactor or brief observation, while a rescue vehicle must erase most of the relative motion so the two spacecraft appear nearly stationary to each other. The mathematics often begins with a boundary value problem. Given a departure point, an arrival point, the gravitational environment, and an allowed flight time, what orbit connects them? In simplified two-body mechanics, this is associated with Lambert's problem, but realistic planning may include planetary perturbations, propulsion limits, navigation uncertainty, communication delays, launch constraints, and the target's future maneuvers. The solution is rarely a straight line, because both spacecraft and Earth are orbiting the Sun, and a rescue craft must enter a trajectory that intersects the lost ship's moving orbit at the proper phase. A faster rescue is not always possible merely by adding more thrust. Shortening flight time usually increases the required energy and delta V, possibly beyond the capacity of available launch vehicles, upper stages, fuel tanks, heat shields, or life support systems. A vehicle launched from Earth must first escape or reshape its terrestrial orbit, depart onto an interplanetary trajectory, perform corrections, match the target's velocity, and still preserve enough propellant for docking, crew transfer, and some form of return or safe destination. Rendezvous guidance has always required careful management of relative position and velocity, and historical spacecraft operations show that meeting a vehicle not originally designed to cooperate can be significantly harder than approaching one equipped with compatible navigation aids and docking hardware. If the lost spacecraft can still navigate and maneuver, it may reduce the burden by transmitting precise tracking data, stabilizing its attitude, conserving docking equipment, and altering its orbit toward a more reachable meeting point. If it cannot maneuver, the rescue craft must absorb nearly the entire velocity matching cost. If the ship is tumbling, physically damaged, venting gas, or surrounded by fragments, close approach becomes more hazardous. Docking ports may be incompatible or inaccessible, and the rescue crew might need to conduct a carefully controlled transfer through an airlock or specialized capture system, all while both vehicles continue moving around the Sun at enormous absolute speed. The rendezvous itself would be performed through small relative motions, often measured in meters per second and then centimeters per second, because in orbital mechanics, gentle approach is created not by stopping in space, but by making two fast-moving trajectories nearly identical. Navigation uncertainty becomes increasingly important as the vehicles draw closer. Ground-based radio measurements may guide the long cruise, while onboard cameras, LiDAR, radar, or optical markers provide relative range and bearing during final approach. Optical navigation has repeatedly improved spacecraft delivery accuracy near planets, comets, and asteroids by comparing observed targets with predicted positions, showing how images can refine a trajectory when radio tracking alone leaves important uncertainties. Time remains the most unforgiving variable. A technically perfect rescue trajectory is meaningless if it arrives after carbon dioxide removal, electrical power, water processing, or cabin pressure has already failed. Mission planners would compare the earliest physically achievable arrival with several survival estimates: an optimistic case in which systems remain stable, a nominal case based on expected consumption and degradation, and a conservative case allowing for hidden failures. These clocks are coupled. Asking the lost craft to make a large burn may shorten rescue time but consume electrical power, attitude control propellant, or thermal margin needed for survival. Waiting for a more efficient launch window may save fuel while costing weeks the crew does not possess. A rapid rescue vehicle might reach the target, but lack the mass required to bring sufficient air, water, medical equipment, shielding, and return capability. Every plan is therefore an exchange among speed, payload, risk, and uncertainty. Apollo 13 is sometimes remembered as a space rescue, but it was more accurately a recovery, conducted with the original crew and spacecraft still on a track that could be modeled, communicated with, and redirected around the Moon toward Earth. No separate vehicle crossed interplanetary space to meet it. A ship genuinely lost far beyond Earth would present a much harder problem, because humanity does not ordinarily maintain fueled, deep space rescue craft waiting on launch pads or stationed throughout the solar system. The exact feasibility would depend on future infrastructure, propellant depots, reusable interplanetary vehicles, habitats near the Moon or Mars, autonomous navigation, high-energy propulsion, and spacecraft designed with common docking and survival standards could all change what counts as reachable. Under present physical principles, however, 3 windows must overlap. Earth must locate the ship accurately enough to predict a rendezvous. A rescue vehicle must possess the energy and time to match its trajectory, and the crew's habitat must remain functional until contact. If any one of these windows closes, rescue may become impossible, even while the other 2 remain open. Earth might know exactly where the spacecraft is, but be unable to reach it in time. A powerful vehicle might be available, but lack a sufficiently precise target state. The lost crew might survive for months, while orbital geometry demands a journey lasting years. And so, the answer is neither a simple yes, nor a simple no. Earth could find and rescue a lost spacecraft under favorable conditions, especially if its beacon, navigation system, propulsion, and life support remained partly functional, and the distance were not too great. But possibility would narrow with every hour that uncertainty expanded, and every kilometer per second of velocity difference that had to be erased. Far away in the darkness, the stranded vessel would not be waiting at a fixed point, like a boat on a still sea. It would be tracing a moving curve through a moving solar system, and the rescue craft would have to enter that same curve with almost perfect timing, arriving not merely where the ship is, but where it is going, carrying enough momentum to follow it and enough life to bring its travelers home. The final fate of a lost spacecraft would not be decided in a single dramatic moment, because space rarely closes a story with the suddenness familiar from storms, collisions, or falling structures on Earth. More often, it allows motion to continue long after control has ended, separating the fate of the people inside from the fate of the machine carrying them. The best possible outcome would begin before the ship had traveled too far along the wrong trajectory. While its clock remained reliable, its sensors still recognized the sky, and enough propellant survived for a carefully measured correction. If repeated observations narrowed the uncertainty in position and velocity, navigators could calculate a burn that did not simply point the vehicle toward Earth, but placed it onto an orbit that would intersect Earth's future position at the correct time and with a manageable arrival speed. The required maneuver might be surprisingly small if performed early, because a slight change in velocity can accumulate into a large displacement across months of travel. Just as a tiny adjustment to the angle of a distant beam changes where it eventually falls. This is the merciful side of orbital mechanics. The same sensitivity that allows a small error to grow can allow a small correction to prevent that growth. Yet every hour narrows the range of recoverable futures. Once the ship's remaining delta V falls below the amount required to enter a safe return or rendezvous trajectory, survival and navigation become separate questions. The spacecraft may still preserve air, water, and communication for a time, but the geometry of return may already be beyond its physical capacity. If it remains gravitationally bound to the Sun, the ship will continue along an elliptical orbit, rather than drifting randomly through a featureless void. Its path may carry it outward toward a distant aphelion, where motion slows relative to the sun, then inward again, as gravitational potential energy becomes kinetic energy. Depending on the orbit's size, one revolution could take years, decades, centuries, or far longer. In principle, the vehicle might eventually pass again through the inner solar system, but returning to the same region is not the same as returning to Earth. The planet will occupy only one small portion of its orbit at any given time, and unless the periods and phases align with extraordinary precision, the spacecraft may cross Earth's orbital distance while Earth is somewhere else entirely. Repeated planetary encounters could alter the trajectory over time, especially if the ship passes close enough for a planet's gravity to bend its path significantly. Such encounters may raise or lower heliocentric orbital energy, change inclination, or redirect the craft into a new region of the solar system. But accidental rescue through this process would be exceptionally unlikely. Gravity assists are useful because mission designers arrange them with exact timing. Without that timing, a planetary flyby is merely another transformation of an already uncertain path. A close approach could even eject the spacecraft from the solar system, or send it toward the sun, although direct impact with a planet or star would remain improbable because physical bodies occupy only a tiny fraction of the volume through which the ship travels. If the spacecraft possesses positive orbital energy relative to the sun, it will follow a hyperbolic escape trajectory, slowing as it climbs outward, but retaining a non-zero velocity after the sun's influence becomes comparatively weak. It would pass the giant planets, then the region of icy bodies beyond Neptune, then the much more distant reservoir associated with the Oort cloud, although the Oort cloud is thought to be sparse rather than a bright shell crowded with comets. Crossing it could take thousands or tens of thousands of years. There would be no visible border announcing that the ship had entered interstellar space. The solar wind would weaken, the surrounding plasma environment would change, and the sun would become another star-like light behind it. But gravity and motion would continue without interruption. The spacecraft would then join the wider gravitational system of the Milky Way, carrying not only its departure velocity, but also the much larger orbital velocity it inherited from the Sun around the galactic center. It would not move through the galaxy as an object detached from all structure. It would follow its own galactic orbit, shaped by the combined gravitational influence of stars, gas, dark matter, and the galaxy's evolving mass distribution. Over millions of years, passing stars could perturb the trajectory, though most encounters would occur at distances too large to produce dramatic effects. A sufficiently close stellar passage might redirect the ship, and, in an exceedingly rare geometry, it could become weakly bound to another system. But ordinary capture is difficult, because an incoming object must lose energy relative to the star, usually through interaction with a third body, gas, or some other mechanism. Without such an exchange, it would most likely pass through and continue onward. The probability of striking a star or planet would remain very small, even over immense spans of time. Because galaxies are visually rich, yet volumetrically empty, the distances between stars are so large that two galaxies can interpenetrate while most individual stars never collide. A spacecraft, far smaller than a star, would usually encounter even less. Long before such distant possibilities mattered, the machine would cease to function. Its electrical systems would not share the near endlessness of its trajectory. Batteries would lose capacity through chemical aging and repeated cycling. Solar arrays, if present, would receive diminishing energy as the ship moved away from the sun, with available sunlight decreasing approximately according to the inverse square of distance. Radioisotope sources would continue producing heat and electricity without sunlight, but their output would decline through radioactive decay and degradation of the conversion system. Capacitors would age, solder joints would fatigue, lubricants would migrate, seals would harden, and radiation would gradually create defects in electronic components and materials. Thermal cycling could expand and contract structures until microscopic cracks became larger. A single failed regulator, corrupted processor, or seized pump might end the spacecraft's active life, even while other systems remained intact. Its final transmission might not be a deliberate farewell. It could be an incomplete packet, a carrier tone fading below the receiving threshold, or a scheduled signal that simply failed to appear. For a time, Earth might continue listening, uncertain whether the silence meant permanent failure, temporary misalignment, or a transmitter operating outside the expected frequency. Eventually, the probability of recovery would become so small that the ship would transition from an active mission to an unresponsive object whose path could only be estimated. The spacecraft's physical structure might persist much longer than its electronics. In deep space, there is little atmospheric oxygen to support ordinary corrosion, no rain, and almost no drag. But the vehicle would still experience radiation, micrometeoroid impacts, thermal stress, sputtering from energetic particles, and slow changes in exposed materials. Paints and polymers might darken, crack, or erode. Thin surfaces could accumulate impact pits. Unprotected internal gases might leak away through degraded seals. If the pressure vessel remained closed, its interior conditions would depend on the sequence of failures that preceded silence. There is no single scientifically defensible outcome for biological material inside, because temperature, pressure, humidity, microbial activity, radiation, chemical composition, and time all matter. A warm, sealed cabin would evolve differently from a depressurized, frozen one, and both would differ from an interior repeatedly heated by sunlight and cooled in shadow. Even the word preserved would require caution, because apparent physical persistence does not mean molecular stability. Radiation would continue altering tissues and materials, while microorganisms might remain active for some period if water and suitable temperatures persisted. Eventually, the spacecraft could become an archaeological object without an archaeologist, carrying manufactured alloys, personal belongings, digital memories, and traces of Earth into regions where no human artifact had existed before. If it remained in a solar orbit, its trajectory might stay broadly predictable for a long time, although repeated close encounters could introduce chaotic sensitivity, making exact long-term forecasts increasingly uncertain. If it escaped into interstellar space, its future would be governed by stellar encounters and galactic dynamics rather than by the sun alone. In neither case would it reach a final edge and stop. Space does not appear to possess a physical boundary resembling a wall around the observable universe. The observable universe is instead limited by the distance from which light has had time to reach us, combined with cosmic expansion. A spacecraft traveling at any plausible human-made speed would remain within the local gravitationally bound environment for spans enormously longer than civilization has existed. Cosmic expansion would not pull it away from the Milky Way in the near or even extraordinarily distant future, because gravitationally bound systems do not expand in the same manner as the large-scale distances between unbound galaxy groups. The ship would continue orbiting within the galaxy unless later gravitational encounters changed that status. Across incomprehensibly long timescales, stellar evolution would alter the surrounding sky. Familiar constellations would dissolve as stars moved. The sun would change, the Milky Way's structure would evolve, and interactions with neighboring galaxies would reshape the local gravitational landscape. Predictions extending into such eras become increasingly model-dependent, but the central mechanics remain clear. Motion continues unless forces modify it, and there is no ordinary process that causes an inert object in vacuum simply to become still. This creates the final separation between function and existence. The spacecraft may lose navigation, then communication, then power, then pressure, yet its center of mass will continue following a lawful trajectory. The machine can stop being a habitat without stopping being a traveler. It can stop being a mission without stopping being evidence that the mission once occurred. And this is the deepest meaning of being lost in deep space. The loss is not always a disappearance from the universe, but a disappearance from every network of reachable choices. At first, the crew can choose among trajectories. Later, they can choose how to ration resources and when to transmit. Later still, perhaps only the automatic systems can choose among programmed responses. Eventually, there may be no remaining action capable of changing the outcome, while the spacecraft continues moving as faithfully as before. The stars will not close around it. The darkness will not swallow it in any literal sense, and time will not erase its momentum. It will simply travel beyond the range where intention matters, carrying the shape of human engineering into a future no human mind can fully picture, until it becomes one more silent object, following the geometry of gravity through the night. Thank you for drifting through the darkness with me tonight. If you enjoyed this quiet journey, please like the video and subscribe to Sleepy Space. Your support truly means more than you know.